Good evening, ma'am. Am I audible to you?
Yes, sir. You are audible, sir.
Thank you, ma'am. Thank you.
Sir, you can start, sir.
Yes, ma'am. Sure. Good evening, students.
Good evening, sir.
Yeah. So today we are going to start our discussion on current electricity. Okay. So now I am sharing my whiteboard with you. Are you able to see the whiteboard, students?
Yes, sir.
Yeah. Thank you so much. So today we are going to start our discussion on current electricity. Current. So can anyone tell me what is the meaning of current here in physics? As far as current electricity is concerned, what is the meaning of current?
So, the rate of flow of charge.
Yeah, absolutely right. So in a conductor, you are having a large number of free electrons. Okay. So let us consider a conductor like this. Okay. Let us consider a conductor is there, and we actually apply a potential difference to the two ends of the conductor. So this is positive polarity and this is negative polarity. And when you apply this kind of potential difference to this conductor, what will happen? The free electron starts moving inside the conductor, okay, and the free electrons carry the charge. So the rate of flow of electric charges inside the conductor is called electric current, okay. So SI unit of this electric current is actually ampere. SI unit is actually ampere, okay, represented by the symbol capital A, and you have to divide the charges flowing through the conductor by the time, then you will get the electric current flowing through the conductor. So this is the basic idea of electric current, and the dimension of this electric current is also A, okay. So this dimension and all, it is very important. Whenever you solve numerical problems related to units and dimensions, you need to have a good knowledge of all the dimensions, okay. The dimensions for the fundamental quantities, at least you should know. Then only you will be able to solve the numerical problems related to units and dimensions. So this is a short introduction about the electric current. So the rate of flow of charges, and whenever the current is given as a function of time, okay, whenever the current is given as a function of time, for example, whenever the charge is given as the function of time, so 1.5 t square plus t. So in this scenario, the charge is given as a function of time. So if you have to find out the current flowing due to these charges, you have to go for differentiation. So I equal to dq by dt. The charge is given as a function of time here. So actually, when I want to find out the electric current, I have to go for differentiation of this equation. So once I differentiate this, what I will get? I will get 3t plus 1, okay, 3t plus 1. So this is how I need to calculate the electric current when charge is given as a function of time. So in these kind of questions, they will be giving you the value of time also. So here they have given charge as a function of time, and they are asking you to calculate the electric current at t equal to 2 seconds, okay. So in this scenario, you have calculated the current equation for current. Now you have to substitute the time value 3 into 2 plus 1, that will be 7 ampere in this case, okay. So this is just an example in which the charge is given as a function of time, and when you are asked to find out the current, you have to go for differentiation of this charge. In this way, you can calculate the electric current, okay. In some cases, you will be given the graph, okay, you will be given the graph, and using the graph, how will you calculate the current or even the charge flowing through the conductor, okay. For example, let me draw a graph here, okay. This is y-axis, and this is x-axis. So here you will be and here on x-axis you are having the time, okay. On y-axis you are having the current. So here the current is there. Current is represented by capital I, and here you have the graph of current versus time, and the curve actually looks like this. Okay, this is just an example. So if you have a curve like this, and the curve actually can touch the y-axis like this also, okay, like this. So in this case, when you find the area, okay, when you find the area covered under this graph, what you will get, it is actually the total charge, okay, total charge flowing. So that quantity you can get when you integrate this quantity I into dt. So if you want to find out the total charge flowing through the conductor, you have to integrate the area under this curve. Okay, you have to integrate the area under this curve. This curve actually represents the variation of current with respect to time, and when you integrate this curve, you will be getting the total charge flowing through the conductor. So this is another method to calculate the charge. Whenever you have a form of graph like this, and the integration limits can vary, okay, for different types of graphs. The integration limits can vary, okay. In this case, you have 0 to t. So here the time is 0, and here the time is t, and here the integration limits are 0 to t. Suppose you have a different graphs like this. Suppose you have a different graph like this. And you are asked to find out the charge flowing between this time t1 and t2. Okay, so here you have time along x-axis and current along y-axis, and you have been asked to find out the charge flowing through the conductor between these time interval t1 and t2. Then you have to integrate the graph between these limits. Okay, so in this case, the total charge can be found out by q equal to I into dt, and the integration limits are t1 to t2. Okay, so this is how you need to proceed with the calculation of current and the charge as well through a conductor. Okay, so do you all understand this concept? Do you all have any doubt actually? If you have any doubt on this concept, you can unmute yourself and you can tell me. Up to this point, if you have any doubt, you can surely tell me. Students, is it clear till here? Up to this point? Okay. Can I move on to the next concept?
Yes, sir. It's clear.
Yeah. Thank you. So for that, I will be opening the next page. Now I am considering the electric current due to circular motion of charges. Okay. So I am considering the concept of average electric current due to circular motion. Due to circular motion of charges. So this is the concept. So if you have a charge moving in circular path, okay, if you have a charge and it is moving in circular path like this, for example, you can have this charge here, okay, the charge is located somewhere here, and the radius of this circle, let us consider as small r, okay, the radius is small r. This is small r. So the charge is moving in a circular path like this, and the velocity of this charge, the linear velocity of this charge can be taken as v, okay. So now I have to find out the current due to the circular motion of this charge. So as usual, I equal to q by p here, okay. Here I am using the capital letter P because I am considering the time period. Time period means the time taken by the charge to complete one revolution. So I equal to q by capital T, okay. So here the frequency of revolution of this charge is taken as n, and that is actually the reciprocal of the time period t, okay. So in this case, when n equal to 1 by t, your I will be I equal to q into n. This is one formula, and as far as this time period is concerned, time period is equal to displacement by velocity. Here the displacement is the one complete revolution. That means the circumference of the circle can be taken as one complete revolution divided by velocity v. So t equal to 2 pi r by v. And now when you want to find out the current, so I is equal to q divided by 2 pi r divided by v. So this will be qv divided by 2 pi into r. I equal to qv divided by 2 pi r. Then you have to substitute the value of v, which is related with the angular velocity, as v equal to r omega. So I is equal to q into r omega divided by 2 pi into r. So when you cancel out the r in numerator and denominator, you will be getting I equal to q omega divided by 2 pi, okay. I equal to q omega divided by 2 pi. So this is how you need to find out the average electric current due to circular motion of charge. So whenever you have the time period capital T like this, then you can calculate the total current I by this equation. I equal to q omega by 2 pi. So the next thing is current density. Okay, the next concept which we are going to discuss is the concept of current density. And it is represented by the letter capital J. Okay. Now, students, do you all have any idea about the concept of current density? Can anyone tell me what is meant by current density? Whatever you know about this, you can unmute yourself and you can tell me here.
So,
Yeah, tell me, student. Tell me. Yeah.
so current per unit volume of the conductor, sir.
Actually, here current per unit area is called the current density. Okay. So current per unit area is called the current density. So whenever you have a conductor, okay, whenever you have a conductor and whenever you have the area of cross section of the conductor as capital A, then the current density is represented by J equal to I divided by A. Current per unit area, okay, J equal to I by A, current per unit area. So that is called current density, okay, J equal to I by A. So this is called current density, and the SI unit, for current density, what it will be? Can anyone predict that? The SI unit for current density?
So ampere per meter square.
Absolutely right. So it is ampere per meter square. Okay, or it can also be represented as ampere meter inverse 2. Okay, so this is the SI unit of this current density. Okay, SI unit of this current density, and from this equation of current density J equal to I by A, can anyone predict the dimensional formula? Dimensional formula. Can anyone predict? The dimensional formula, can anyone predict, students?
Sir, ampere, yes, sir.
Yes. Then you have area, right? Okay, you have area also. So
L
J
square.
equal to, yes, tell me. For current, it is ampere. Okay, student, you should not confuse. Actually, here you have this A as the area of cross section. Okay, but here for the dimensional formula, you have current in the numerator for this equation. So for that, the dimensional formula is A. This A is the dimensional equivalent of this current. Okay, you should not confuse this A with this A, because this A is the area of cross section. Okay, and this is the ampere here, and this A is actually the dimensional equivalent for this current. So ampere, for ampere you have the dimensional equivalent A, and for area of cross section, what is the dimension here? Can anyone tell me? For area of cross section, area, yeah, tell me. Yeah, tell me.
L squared, sir.
Yeah, but here it is in denominator, right? So,
This is
so this will be L power
so
minus 2.
L minus 2, sir.
L power minus 2. Okay, dimensional formula is equal to A into L power minus 2. So this is the dimensional formula for the current density. Okay, so you have different ways to calculate the current from the current density actually. So in vector form, how will you calculate? In vector form, so I equal to J dot A. Okay, this is one method. I equal to J dot A. And another method to calculate the current from the current density is I equal to integration j dot dA. Okay, and this integration is over the surface for which you calculate the current. So these are the several methods to calculate the current from the current density. So I equal to j dot A, and you can also integrate that I equal to integral j dot dA. The integration happens over the particular surface, yes. So from this you need to calculate the current from current density. And from this equation, what you can understand is the current density is actually inversely proportional to the area of cross section. Okay, current density and area of cross section are inversely proportional. Okay, so these are all the important concepts of current density. Okay, do you all understand this? Any doubt you have up to this point? Students, any doubt you have
Yes,
up to
sir.
this point?
Sir, no, sir, no doubt, sir.
Okay, okay. Even if you have any doubt, you should not hesitate to ask your doubt in the class. Okay, because you are actually learning the concepts. Okay, so you should not have any hesitation in asking your doubts. Right. Now I will be discussing the next concept, that is the concept of drift velocity. The concept of drift velocity. Now, students, can anyone tell me what is mean by drift velocity? Anyone have any idea regarding this? The drift velocity. Students, anyone have any
Sir?
idea? Yeah, tell me. Yeah, tell me.
Sir, sir, in the presence of an external field, sir,
Yeah.
like when the charges are flowing, right, sir?
Yes.
When it's flowing from one terminal to the other terminal, sir, the
Yes.
electrons, they do not like move in a random motion, sir. They rather drift from one terminal to the other terminal, sir. That
Yes.
velocity with which they drift, sir, that's called drift velocity, sir.
So you can actually refine your explanation little bit, but still it's no issue. Okay. What is mean by this drift velocity? So let us discuss a little bit regarding that, and then we shall move on. So here I have shown you a conductor. Okay. So let us consider this conductor. It is in cylindrical shape. And what I am doing is I am applying a potential difference to this conductor. Okay. I am applying a potential difference. This is the positive potential. This is the negative potential. Okay. So I have the positive potential like this and negative potential like this. So I am applying a potential difference to this cylindrical shaped conductor. What will happen here? Due to the presence of the positive potential, okay, due to the presence of the positive potential, inside the conductor there are a lot of free electrons. Okay, this is a good conductor of electricity. So inside a conductor there are a lot of free electrons. So when I apply this kind of potential difference to this conductor, what will happen? Due to the presence of this positive potential, okay, actually the electrons, since they are negatively charged, the electrons actually start moving in this direction. Okay, why it is so? Because you have a positive potential here. Okay, you have a positive potential here at this point. So due to the presence of this positive potential, the free electrons inside the conductor are attracted towards this side. So the free electrons start moving towards this side. Okay, but what about the direction of external electric field? So the direction of external electric field is actually like this. So the direction of external electric field is actually along this direction. Okay. So due to the presence of this potential difference, the electric field is in this direction. The electrons actually move in the opposite direction. So without the potential difference, actually all the electrons are in random motion. So the average velocity of the electrons is actually 0, because in the absence of this potential difference, the electrons are in random motion throughout the conductor, and when you apply this potential difference, the electrons, they start moving towards the positive potential, and the movement of electrons is channelized now, and these electrons, while moving inside the conductor, they begin to collide with the positive ions in the conductor. Okay, so they begin to collide with the positive ions in the conductor, and after making a lot of collisions with the positive ions inside the conductor, the electrons will start moving with the common velocity. Okay, all the electrons inside the conductor, due to the presence of this potential difference, they will move towards the positive potential, and in the process they actually collide with the positive ions inside the conductor. After making a lot of collisions inside the conductor, the electrons will start moving with a common velocity, and that velocity is actually called the drift velocity. Okay, so the common velocity with which the electrons move is called the drift velocity, and that drift velocity is actually represented by v suffix v. It is a vector quantity. Okay, the drift velocity is the velocity with which the electrons move inside the conductor after making a lot of collisions. Okay, so what will be the force acting on the electrons? So that force is actually F equal to minus E into capital E. Okay, F equal to minus E into capital E. So let me erase it. So let me show it in a different color so that you can understand this. So the force acting on the electrons is given by F equal to minus E into capital E. Okay, because F equal to Q into E, that is the formula which we get from Coulomb's law. Okay, so here the charge of the electron is negative, so we use minus sign. F equal to minus E into capital E. This is the force acting on each electron. So now what is the expression for this drift velocity? For that we will be discussing now. So if the time interval between two successive collisions of this electron with positive ions is considered as tau. Okay, so tau is the time interval, okay, between two successive collisions. time interval between two successive collisions, and this tau is otherwise called relaxation time. Okay, relaxation time, and this is the time interval between two successive collisions. And we all know very well that in general the velocity is given as the product. Okay, in general the velocity is given as the product of acceleration and time. Okay, acceleration and time. So here, for calculating the drift velocity, Vd is equal to acceleration into this relaxation time. Okay, Vd equal to a into tau. This is the expression for the drift velocity, and this acceleration can be written as minus E capital E by m into tau. So let me write it here. The expression for this drift velocity is Vd equal to minus E capital E divided by m into tau. Okay. So this is the expression for drift velocity, and here you can see. Let me write it right. So this drift velocity can be written like this. So Vd equal to minus E capital E by m into tau. So this drift velocity, you have a negative sign here. Okay, in vector form you have a negative sign because the electric field and the movement of electrons is in opposite direction. So the drift velocity and the electric field is in opposite direction. So we actually get a negative sign here. Okay, so this is the expression for drift velocity, and using the expression for drift velocity, we can actually find out the relation between the current and the drift velocity. There is a derivation for that, and we are not actually going to discuss in detail the derivation. I am just writing the final expression for the relation between the drift velocity and current. Okay, I equal to NEA into Vd or NAD into Vd. So here what is meant by N? N is nothing but number of conduction electrons in the conductor. Okay, number of conduction electrons per unit volume. Number of conduction electrons per unit volume. So all these formulas are important for you while solving the numerical problems. So N is the number of conduction electrons per unit volume, and A is the area of cross section of the conductor, and E is the electron charge, and Vd is the drift velocity. So this is the relation between the current and drift velocity. Okay, current and drift velocity. So now from this you can find out the expression for current density also. So how will you calculate the current density? So just now we have discussed. Okay, so J equal to the expression for current density we can obtain here. That is J equal to I by A. Okay, J equal to I by A. So this equation, what you can do? So this equation you have to divide by A in order to get the expression for current density. So J equal to I by A. So that will be NE into VD. Okay, J equal to NE into VD. This is the relation between the current density and the drift velocity. I hope you all can understand this concept, the relation between the current density and the drift velocity. Do you all understand this, students?
Yes, sir.
Yes, that's great. So now I think we have to discuss the concept of resistance. Okay, we have to discuss the concept of resistance. What is meant by resistance?
Opposition.
Yes, in general, resistance is nothing but opposition. Okay. So in terms of current electricity, resistance is the opposition offered by the object. Okay. So resistance is the opposition offered by the object to the flow of electrons. So the opposition offered by the object to the flow of electrons. That means even if you apply some potential difference to a conductor, okay, it is not easy to move inside the conductor because inside the conductor there are many positive ions, and when the electrons start moving inside the conductor, they start colliding with the positive ions. Okay, so in that way, the conductor offers some resistance to the flow of electrons inside the conductor. So that is actually called resistance. So this is the literal meaning of resistance for a conductor. And in terms of equation, do you know any equation for the resistance? Do you know any formula or equation for the resistance, students? Do you know any formula or equation for calculating the resistance? In terms
Sir,
of
R is
potential,
equal to V.
yeah, tell me.
Sir, R is equal to V by I, sir.
You are right. So R is equal to V by I.
Yes, sir. Ohm law formulas.
This is called Ohm's law. Okay, this is called Ohm's law. So here the statement of Ohm's law is actually constant physical conditions. Okay, so at constant physical conditions, R equal to V by I. Okay, this word is very important at constant physical conditions. So whenever the physical condition changes, then this R equal to V by I is not applicable. So this R equal to V by I is applicable only in cases where the physical conditions do not change. Okay, so R equal to V by I, and sorry. So R equal to V by A, and when you plot a graph, okay, when you plot a graph between the potential difference and the current, so here you have a potential difference along y-axis and current along x-axis. Whenever the conductor obeys this kind of relation, okay, that is the VI graph for this conductor is a straight line. That means the conductor obeys Ohm's law. So this kind of behavior you can see in case of ohmic conductors, okay. Ohmic conductors means conductors that obey Ohm's law. And the another condition is physical conditions should remain constant, then only this Ohm's law is also obeyed, okay. So whenever the VI graph is a straight line, then that is called ohmic conductor, okay. So when it is not a straight line, they are called actually non-ohmic conductors. In the graph for potential difference versus current, when it is not a straight line, so the conductor is actually called non-ohmic conductor, okay. So for resistors, actually you use different symbols, okay. For resistors you use different symbols. So for a fixed resistor, your symbol is like this. Fixed resistor, your symbol is like this, okay. And when you use a variable resistor, you actually put an arrow mark over the resistor, okay. That means it is variable, the resistance is variable, okay. And potential difference circuit is also one example. Potential divider is also one example. So there the symbol is like this, okay, potential divider. So this is also a concept of resistance, and this is all you need to know about the Ohm's law and the ohmic conductors, okay. Okay. Now, what are the limitations? What are the limitations of Ohm's law? So the limitation of Ohm's law is very simple. The physical conditions, when they remain constant only, this Ohm's law is applicable, okay. Limitation of Ohm's law is nothing but the physical conditions should remain constant, okay. the physical conditions remain constant. Then only you can use the Ohm's law, otherwise you can't. This is the limitation of Ohm's law. Okay. Right. And now I will be discussing the next concept, that is factors affecting the resistance of a conductor. Okay. Factors affecting the resistance of a conductor. So what are the factors affecting the resistance of a conductor? That is, R is directly proportional to L, inversely proportional to area of cross section. So that means R is proportional to L by A, and when you remove the proportionality, you have to put a constant. So here, remove the proportionality and put a equal to sign. So rho into L by A. R equal to rho into L by A. That means the length of the conductor is directly proportional to the resistance, and the area of cross section is inversely proportional to the resistance. These are the factors affecting the resistance of a conductor. And when I remove this proportionality, I have to put an equal to sign, and after that I am putting a constant here, that is rho. What is the meaning of this rho? What is this rho? Can anyone tell me?
Resistivity.
So resistivity for the conductor.
Yeah, you are right, resistivity. And what is the meaning of that? The resistivity, can anyone tell me? Yes, students, the resistivity meaning, can anyone tell me?
So,
Yeah, tell me.
so the resistivity of conductor is numerically equal to the resistance of when the conductor is of length 1 meter and area of cross section 1 meter square.
Yeah, so here you can define the resistivity from this equation itself. So if the length of the conductor is 1 meter and the area of cross section is 1 meter square, okay, in that case R equal to rho, that means the resistivity is numerically equal to the resistance of a conductor, which is having a length 1 meter and the area of cross section is 1 meter square. Okay. So this is the definition of resistivity. And now I am asking you a question. Which one is having the least resistance? A thicker wire or a thinner wire? Thicker wire or thinner wire? Which one is having the least resistance? Let me ask you a question. Thicker wire or thinner wire? Yes.
Sir, less resistance, sir.
Which one is having the least resistance?
Sir, thicker wire, sir.
Thicker wire is having the least resistance. Why?
Sir, resistance is inversely proportional to the area, sir. So for thicker
Oh.
wire, area is more, sir. So resistance will be lesser.
Yeah, you are absolutely right. So for a thicker wire, the area of cross section is more. Okay. So for a thicker wire, the area of cross section is more. So here, area, okay. Area of cross section is more. So area of cross section is more for a thicker wire. So that means here resistance is inversely proportional to area. So area is more. So thicker wire has less resistance, while thinner wire has more resistance. Okay. Okay. Now, what is the need for introducing this rho in this equation? So we have to remove the proportionality and putting a constant here. So as you can see, the resistance depends on these factors, the length and the area of cross section. So here actually the resistance is not constant even for a material of same type. Okay, if you take a copper wire of 1 meter length and another copper wire of 10 meter length, both of the same area of cross section, your resistances will be different, right? Because of the change in length. Okay, the same material, the same copper wire, when you take different lengths, that is 1 meter for one copper wire and a 10 meter for another copper wire, the same material will have different resistances. Similarly, when you take a copper wire of 5 meter square cross section and another copper wire of 50 meter square cross section, then you will be having different resistances for the same material, same copper wire. So how can you differentiate the ability of materials to offer resistance to the flow of electrons? For that only we actually introduce the concept of resistivity, because resistivity is a constant for a particular material. If you take copper, the resistivity is constant, whatever may be the length or area of cross section, because we actually consider 1 meter length and 1 meter squared area. Okay. For different materials, you can take 1 meter length and 1 meter squared area of cross section, and for that materials, when you calculate the resistance, you will be getting resistivity. So resistivity is a constant for a particular material. In this way, you can actually differentiate the ability of different materials to offer resistance to the flow of electrons inside it. Okay. So that's why we actually introduce resistivity. And before that, I will be asking you a question. What is the SI unit of resistance? What is the SI unit of resistance?
Ohm, sir.
Ohm. Yes. So what is the SI unit of resistivity?
So ohm meter, sir.
Ohm meter. You are right. So ohm meter is the SI unit of resistivity. Okay. So these are the concepts which we have discussed now, and usually when we talk about the area of cross section of a wire, we always consider that the wire is having a circular cross section. Okay, the wire is having a circular cross section. So circular cross section means, what is the formula for calculating the area of a particular wire? Circular cross section means, what is the area? What is the formula for calculating the area? Can anyone tell me?
Pi r square.
Yes, you are absolutely right. So that is pi r square, where r is the radius. okay, of the cross section of the wire, and circular cross section area you can calculate using the pi r square. So area of circular cross section is pi r square. In numerical problems, whenever you are asked to find out the circular cross section area, you have to use this formula only, pi r square. Okay. So before winding up today's session, I will give you the dimensional formula for resistivity. Okay. Dimensional formula for rho, that is resistivity. So that is m power 1, L power 3, T power minus 3, and A power minus 2. Okay. So m power 1, L power 3, T power minus 3, and A power minus 2. This is the dimensional formula for resistivity. Okay, and we shall keep it this much for this session. And have you all attended the test, students, last week? The test on electric potential and capacitance.
Yes, sir.
You have some doubts, right? On some
Yes, sir.
numerical problems.
Yes, sir.
Okay. In the next class, you can tell me what are the questions for which you are having doubt. We can discuss the solutions for the numerical problems for which I gave you test, okay, last week. So for whatever numerical problem you are having difficulties in solving, you can inform me in the next class so that we can discuss the solution for the numerical problem. Okay. So now let us keep it this much for this session, and we shall meet again in our next class. Thank you so much, students.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.